In our previous lessons, we discussed supervised method to train machine learning algorithms. How we can use machine learning models to solve classification problems. We discussed about binary classifiers, multi-class classifiers. In this lesson, we are going to discuss and work out a problem to solve multi-class classification problem using logistic regression algorithm comes with scikit-learn machine learning library. The dataset used in this work is iris flower dataset. The iris dataset or iris flower dataset is one of the most famous datasets used in studying and discussing the concepts of statistical learning, data science, and machine learning. The dataset contains 50 examples each from 3 types of flowers: Iris setosa, Iris versicolor, Iris vegetatica. There are 4 attributes: sepal length, sepal width, petal length, and petal width, all measured in centimeters. In this diagram, you can see how they are measured in actual flower. I'm not a biologist, so I don't know much about these measurements or these flowers, but we can work it out, the machine learning problem, and try to understand the data from the descriptions provided by these researchers and different articles. The iris dataset was first introduced by the British statistician and biologist Ronald Fisher in his 1936 paper, The Use of Multiple Measurements in Taxonomic Problems. You can download the dataset from many different sources. In this lesson, I will get you introduced to 2 versions of it. One you can download from the UCI machine learning repository. I will provide the link to download in this notebook. And also you can get the same dataset from the scikit-learn datasets. Let's begin our data exploration task before we are attempting any machine learning applications. You can read more about this iris flower dataset from the Wikipedia article or from the UCI machine learning repository link I provided in this notebook. First, let's see how we can download the dataset from UCI machine learning repository and prepare it for our work. So the dataset download link you can find in this notebook directly from the UCI repository. So you can provide that as a file path to Pandas library. So Pandas read CSV, we already explored in multiple lessons previously, capable of downloading files directly from URLs. Here we are downloading it. So that data file comes as a CSV file. Even the extension is not CSV, the format of the file is CSV. I already opened and checked that. And that does not come with any headers, no column headers in the file. Therefore, we need to provide column headers. Like any other data source you will be dealing with, you have to consult the data description. So in the data description of this iris dataset, it contains, there are 4 columns, 4 feature columns, and 1 column to indicate which flower type it is. And the first 4 columns are sepal length, sepal width, petal length, and petal width. And the last column is flower class. So we assign these 5 column names to the data frame after we load. And then we can check how many rows, how many columns in this data set. If you want to go back to how to do exploratory data analysis in detail, please go back and review the video lesson about exploratory data analysis. So I will execute these steps to load the data from the UCI repository using the URL, and then load into Pandas data frame, assign column names, and then check how many rows and how many columns. At last, in this cell, I'm going to print first 5 rows using the head function. Let's execute that. Okay, so now we see data is being loaded to our Jupyter Notebook environment, and we can see the first 5 rows. Alright, so we confirmed we have 150 rows and 5 columns in this data set. They were properly labeled by column names we provided, and we have all the row indexes assigned by the Pandas data frame. If you want to load the same dataset from the scikit-learn dataset, which comes as a built-in library module, submodule, it's called datasets. Under that, you can import the relevant functions to load the iris data using load iris. So load iris will load your dataset as a class or object into your iris variable, like we shown here. And then you can extract required elements of the dictionary. You can consider that as a dictionary. You can extract relevant fields. So one of such field is flower class, which is your target variable, which comes as an array or list item. And the data you can extract as a two-dimensional array or list, and then you can convert into a data frame, like shown in this line number 7. Then like we did before, we always need to check how many rows and how many columns as soon as we get the dataset. I will execute this and show you how we can load the dataset from the built-in scikit-learn datasets. After we do these steps, you will see you load the dataset, and the dataset is properly loaded, same as you loaded from the UCI machine learning repository we did before. This dataset also contained 150 rows and 5 columns. In the rest of the notebook, I'm going to use the dataset loaded earlier from UCI machine learning repository. Let's try to explore the dataset. First, we wanted to do some descriptive statistics. I'm not going to discuss in detail about descriptive statistics, but I'm going to apply the describe function from Pandas data frame and then get some descriptive statistics from each column. So let's try to apply that here. If you wanted to review a detailed lesson about descriptive statistics, I highly recommend to go back to exploratory data analysis lesson and review the content there. So let's try to apply the describe method from Pandas data frame. So our data frame name is data. Here we get, for each numeric column, we get how many value counts, what is the mean value of each numeric column, what is the standard deviation, what is the minimum value, and then we can get the 25th percentile, 50th percentile, which is mean, median, and 75th percentile and maximum value for each column. This table itself provides very useful information about your data set. It can give some insights into the data distribution and the range and many other things you would like to know when you get the data set. So this will help you to further analyze as well as to decide what type of methods you need to use in processing the data set. We will try to explore it more visually now. We wanted to see what is the proportion of each flower class, because our describe method did not return us any details about the 5th column, which is the class. We saw that value is a string value. So if we wanted to visualize the data, we can use pie charts in Pandas plot. So how we do that? First, we need to get value counts. Let me execute that first before we are going to execute the next one. So let me create a new cell. So you can create a new cell here and first execute value counts from the Pandas series. So flower class is a column name, and when we take out the flower class from the data frame, we get a series. Then you can call value counts. This will return a frequency table, how many values from each category in this column. So this column had 3 different categories. We knew that from the data description. These are the 3 different flower types. So each we had 50 different rows, 50 rows each. So I will delete this because we already printed above. So now we wanted to see this in a visual form as a pie chart. So we can call the result of this value counts will be another series, and we can call the Pandas plot function. We have to provide kind of the plot is pie, which indicates a pie chart. And then if you wanted to print the percentage value inside each segment, you can provide the format you wanted to print. So the parameter to specify that is auto PCT. The auto, like the PCT stand for percentage. So if you provide here, like what I provide here is print the numbers to the first decimal point, because the percentages are floating point numbers. So it will print, it's obvious, 33.3 because we have 50 each. So we have the percentage is printed here. Now let's look at how we can generate a bar chart or bar plot for the same value counts. For that, we can call a Python plot function, and we can specify kind of the plot is bar. So let's execute that. So we get a bar chart here. So this has no interesting things to observe because we know like each type of flower we have same amount of count. But if you wanted to use the same thing for a different dataset, bar charts could be very useful. To visualize how the data distribution looks like for each numeric variable in this dataset, we can use kernel density estimation. So we can plot all of these kernel density estimation in the same plot. This is how we can do that. So we have to specify which column, and then we can invoke the plot function in pandas. That comes with pandas series or data frame. You can use the plot function. For this, we use for pandas series, we isolated. If you wanted to learn more about slicing pandas data frames in row level and column level, go back to Python basics lessons we discussed previously. So here we are taking a series out and call the plot function, and we provide kind of the plot is kernel density estimation or KDE here. Here I'm enabling the legend. I'm saying legend is true because I wanted to let the reader of this object, reader of this report, to know which type of plot it is. Let's execute this cell. So here we get the kernel density estimation plot on the same plot window. So we also have the legend to indicate which color is coming from which column. We see how each numeric data column is distributed. So you can also use histogram to visualize the distribution, but if you want to do a histogram, it's a good idea to plot them individually, not everything on the same plot. So now we can analyze the variable distribution by each flower class, means what is the flower type. So let's look at let's first isolate the data or rows for flower class iris versicolor, and then we can take the column sepal length, and then we can plot the kernel density estimation for the flowers belong to iris versicolor. We can do the same thing for iris virginica and iris sedosa. So what we should expect here, should expect 3 different curves for the same variable, but each curve should describe the data distribution for that variable by the flower class. Okay, so there's nothing new here from our previous cell. So let's execute in one new thing here. So we have to provide a label for this one, because the pandas is not automatically taking the legend. So we have to provide the label which flower class it belongs to, so that we have to manually provide. So here I'm providing iris versicolor, iris virginica, and iris sedosa as the label. So let's execute this cell and see how the data distribution for sepal length by different flower class. You see, there's a nice separation between 3 different flower classes for the variable sepal length. So what are the observations you can take from here? So iris setosa peaked at a lower value of sepal length than iris versicolor, and iris versicolor peaked at a value lower than iris virginica. Let's explore the same for sepal width, petal length, and petal width. I already added the label and legend true for each of the cell below. So let's try to first explore the sepal width, how the distribution looks like for different classes. In the distribution for sepal width, we see Iris versicolor and Iris virginica. They are peaked at closer values of sepal width, but Iris setosa is a little bit higher than the other two, peaked at a higher value than other two. So let's see what it looks like for petal width length. Okay, so this has a very good separation. Iris setosa, the distribution is very narrow compared to other two and peaked at a lower value than Iris versicolor and Iris virginica. Iris versicolor peaked at a lower value than Iris virginica. And the spread of the distributions Iris versicolor and Iris virginica should be higher if we compute that than the Iris setosa. So this information we can derive from this descriptive statistics if you're going to get the mean and median by the flower class. So mean and the standard deviation by the flower class. Okay, so now let's look at the last one, petal width. The distribution for petal width shows a similarity with the petal length distribution we saw earlier, but of course they are in a different scale. So the x-axis or the values of the petal width are different than petal length, but the distribution and which one is the lowest and which one is the highest peaked, so they are very similar to the petal length. Okay, so let's try to generate the correlation matrix between each of these numeric variables. I'm going to use correlation function from a pandas data frame, so which is .corr. So that's a function you can call in pandas data frame if you have numeric variables. So I'm going to provide 4 numeric columns: sepal length, sepal width, petal length, and petal width. And also I'm going to provide the flower casts this time, just to see like what it will give us. All right, and then in the next step in line 4, you can see on the screen, I'm going to plot the correlation matrix in a heat map Seaborn from the Seaborn library. I'm going to annotate that heat map with the correlation value. Means each cell of the heat map will be displayed the correlation value, and the format of that display value will be with two floating point numbers with 2 decimal places. We discussed about these heat maps in our Python lesson before, how to use Seaborn and matplotlib for generate data visualization. If you wanted to go back, you have to review that lesson as well. So after all, we are going to print the result returned from the correlation function, which will print the correlation matrix, and we will visualize how the table looks like, as well as the heat map from executing this cell. So let's execute. All right, so it printed the matrix first, or the data frame first, and then the heat map second, but it's not the same order as we compute. But anyway, so now we have the correlation matrix as a data frame returned from pandas data frame correlation function called CORR. This shows the correlation between each 4 numeric columns with each other. You already have had a discussion about correlation matrix. If you wanted to review that, you have to go to the data exploration lesson we did before. But a few things I will highlight. So correlation with a variable for a variable itself will be 1. So that's why you see the diagonal always 1 in the correlation matrix. Correlation with another variable with another variable will indicate what type of correlation you are having. The negative correlation means when you are increasing one variable, other variable decrease. So that's the trend. And if you have a positive correlation, that means when you are increasing one variable, other variable can also increase. If you have a value close to 1 or -1, that means you have a high correlation. If you have value close to 0, that means you have a weak correlation. For example, sepal length and petal length. Also, the petal width and petal length, you have a very high correlation. And sepal length and sepal width, you have a weak correlation. So we can see how the seaborne heat map will visualize the same correlation matrix. You will see the value of the correlation coefficient will indicate by a color scale. Very low values towards negative side will be darker, and very high values towards positive side will be lighter in the scale, and the middle value is kind of a red pink kind of red color, right? So so you will see this color scale, and this heat map you can use to give a nice visual in a presentation, or if you wanted to understand the correlation matrix and the trends from the correlation matrix, you can use the color heat map. Okay, so everything we discussed so far is about data exploration. I just brought up few of the techniques and methods we discussed previously, just to complete this notebook and add some content to the exploratory data analysis while we are discussing about this iris dataset. We are at a position to start building machine learning model for this classification problem to classify the type of the flower based on its characteristics or the measurements taken by the scientists. First, let's look at the dataset. Let's take a random sample of 5 rows out of the dataset. You can use sample method of function in the data frame object. So here we call data.samples, and we specify how many samples we need to draw from the dataset. If you specify a number of samples, it will give you the same number of samples out, also number of rows out. If you don't provide any parameter into this function, then it will draw just one sample out of your dataset, means one row. Alright, so let's understand what are the features or X variables and the target variable we should use in this classification project model building. That is very important. Before you begin any machine learning model building process, you clearly need to understand what are the features you should be using. If it is a supervised machine learning model, what is your target variable? We executed this cell. It will assign list of column names as list of strings into variable name X variables. And then we create another variable called Y variable, which also contains a string, which is like flower class. So that contains our column name for the target variable. After we identify our X variables and Y variable, let's try to explore the concept of train test split. In our previous lessons, we discussed why we do train test split. In brief, I can explain to you as a review. Think you are taking a class with a teacher. The teacher, when teacher having a lesson with you every day, so he or she will give you a quiz. At the end of the lesson, teacher will also share you answers. What you can do with these questions and answers, you can memorize the questions and the answers. When you get the final exam after you're done with all the course materials, teacher will give you an exam, and if the questions are same as the questions you received in a daily quiz, you probably will answer better by memorizing the answers. What if teacher gave you slightly different questions or questions you never seen before? That is a good measure for the teacher to evaluate whether you know the subject or you learn the subject from this course or not. Same as for a machine learning model, we have to keep one dataset for training, same as your daily quizzes, with known outcome is your Y variable, same as the question and answers for those questions in the daily quizzes a teacher is going to share with you. So those X variables and known Y outcome for the training dataset will be used to train your model. Same as the teacher is going to teach a student about a skill or a subject concept. Then we have to keep another set of questions out from your dataset, which is your testing dataset. So those testing datasets, you also know have the answers and you have the features. What you are doing is, after training the model, you are going to test the model or evaluate the model with a testing dataset, which is never being part of the training. If your model is trained well, or if the model is performing well with your application, your testing dataset should provide a good outcome. Means the model should predict into a good accuracy level. So that's the reason we are using the train test split method. So here what we are doing is using the scikit-learn model selection train test split function to do this train test split for us. So what it is doing is it's randomly dividing your dataset into two parts. What is the proportion of each part can be decided based on this parameter. So what we are instructing this function to do is make our test sample size is 33% or 1/3 of the total dataset. And then we are providing our X variable data frame and Y variable column or the series. You can also provide two-dimensional NumPy arrays for your X variables and one-dimensional NumPy array for your Y variable. Once we do that, we can verify what is the size of our training and testing data sets. So this is why we are using the trained size and test size. This is another important information you need to keep for future use. When you are training any model in your machine learning project, you should know, or you should report, or you should record what is your training dataset size, what is your testing dataset size, along with other information about your training process. We will discuss this in detail in the model deployment in our course. All right, so then let's execute this cell and then try to print what is your training dataset size and testing dataset size. We initially had 150 rows. Now we divided our training dataset size to 100 and our testing dataset size to 50. So this validates our proportion. We have 1/3 of training, 1/3 of testing and 2/3 for train. Let's go to the next section. In this part, what we are doing is we are training a multi-class classifier. A multi-class classifier can classify your observation into more than two classes. We previously discussed about binary classifiers, which you can classify your observation into one out of two, or you can say whether it belongs to this class or not to this class. Logistic regression by design can provide a binary classifier. So it can predict the value close to 0 or close to 1. So based on the value between 0 and 1, we can decide whether your observation is belong to which class, 0 or 1. How the scikit-learn implement this multi-class classifier model, we will discuss after we went through this model building process. I will give you some details about how it implements. The implementation method we call one versus rest. Means it will, if you have 3 classes to predict, it will build 3 models and predict for each class whether an observation belong to that class or not. So that's why we are calling rest. So one class versus rest. So this will happen for all 3 classes in this example, and those 3 models together will make predictions on each observation, and at the end a combination of these results coming from 3 models will be delivered to you as the total outcome for that observation. Okay, so that's about little detail ahead, but let's try to create the model and train the model using the training dataset we created. To create logistic regression model, you need to import the logistic regression class. That's what you can use to construct or create the model object. So here we are going to create the model object. So that model object is named as model here. And then we are training the model by calling the function fit. In scikit-learn, we know almost all the models will use the fit function to train the model. So then we provide our X dataset or features and Y dataset or our target variables for each feature set. Since this is a supervised machine learning, we have to provide both X and Y. All right, so let's go to the next step. Let's execute this first, and nothing is going to show or display to you because this is just creating the model object and training. Since we have a very small number of data points, so the training process is much faster. You will see the process is done instantly. So now let's try to get some model parameters out from the trained model. So the features you already identified before. So what are the features or feature columns from the dataset? I'm going to display that anyway as a list. Then next, let's try to get some attributes out of the model object directly. So the model contains an attribute called classes underscore. So that will give you a list of class labels the model will predict. And then the next attribute you can get from the model object is coefficients. The attribute name is coef underscore. So that will give you the coefficients will be used to fit the logistic regression equation. What do you get here? You get a matrix with 3 rows and 4 columns. So what they are belong to. So normally you would expect one row with 4 variables or 4 different coefficients, one coefficient for each feature, right? So we discussed about the logistic regression equation and how you construct logistic regression equation along with the linear regression in for regression problems. So here I hope you remember that. If not, please go back and review that lesson. So here we get 3 rows, means each row is for each model I described above. The first model will decide whether your observation belongs to iris setosa or not. Okay, and then the second model will decide whether your observation belongs to iris versicolor or not. And third model will decide whether your observation belongs to iris virginica or not. So these are the coefficients for these 3 models. So each model will have these variables for variables, and the parameters or the coefficients for each 4 variables will be different. Okay, so that's why the coefficient metrics can give you in this multi-class classification problem with logistic regression. There's another attribute will be useful if you wanted to construct the equation later, the logistic regression later. So it will be useful to know what is the intercept. To get the intercept out of your model object, you have to call model.intercept underscore. If you do that, you will get 3 values. So what are these 3 values belongs to? So each value belongs to a model. The first value belongs to the first model. Second value belongs to the second model. Third value belongs to the third model. So we know what are those models previously we discussed. If you want to know about that, you can rewind back and you can listen to the discussion before. So now our target is to create a data set with these coefficients and intercepts. So what we want to know is we want to record or report this information in a more presentable way. So that's why I'm trying to create a data frame out of these coefficients and intercepts. So let's try to do that. So here it will tabulate variable coefficients along with the variable names as columns for each class. So that class you now know this class means the model to determine whether that observation belongs to this class or not, with the coefficients and the intercept for the logistic regression equation. You have the logistic regression equation below as well. You can see the C value or Z is what you can describe from by constructing the logistic regression equation. Here I have an example logistic regression equation, not exactly the same one, could be the same one as well, but it will be slightly different numbers, but you can see how the logistic regression equation can be constructed using this information. The bottom example is for one model. Okay, so you can check that out in your own notebook, or you can create your own equation. It's very simple. You can create by using the looking at the data frame. All right, so now try to understand better what I mean by the one versus all or one versus rest classifier. So each classifier we represented by each row will be a binary classifier, like I mentioned. So that will classify whether your observation belong to one class or not. To demonstrate that one versus rest classifier, let's build one classifier at a time. So the only one, just for the demonstration purpose. So I will create a new data frame for new feature data frame for train. I call is xtrain demo. I'm trying to explicitly copy the xtrain dataset to the xtrain demo. And same as that ytrain demo, and I also do xtest demo and ytest demo. So I'm simply copying things. So this is how you can explicitly copy a pandas data frame to another. Because in some situations, this is another side note, some situations pandas will not copy your data frame in memory, but it will copy a reference to a new variable. It will put on a new variable. If you made some changes, it will also change the original location. If you have a very large data set and also you wanted to make changes while you are executing things, so that's okay. But if you want to reuse the same data set and start from the beginning in later in your code, you probably need to copy your data frame. Okay, so I will execute this now. And then what is our goal? We wanted to create a binary classifier. So that classifier we should classify whether any observation provided into the model belong to Iris virginica or not. If it belongs to this Iris versicolor or Iris setosa, it should say 0. If it belongs to Iris virginica, it should return 1. So that's what we are doing. So then we have to convert or transform our target variable or y variable with this condition. So how we can do that? You can use np-var function or numpy-var function, like we discussed in one of our previous class, or you can easily use this replace method in your data frame object. To call the replace method, you have to provide a dictionary of the changes you wanted to make in the data frame the column values. So here ytrain is not a data frame anymore, so it's a series. If you wanted to double check what is ytrain, so we can check that. So how we can check that? We also discussed this in detail. So you can use the type function, the built-in function, and you can pass the variable name, and then it will give you what type your variable belongs to. So it will show you your ytrain demo is a series. In a series, you can directly call the replace function. So what it provide to replace is you have to provide the dictionary. So which value to be replaced with which value. So key will be the current value in your column, and the value in this dictionary item will be the value you need to replace. Okay, so if you have Iris virginica, the value it will replace by 1. If you have Iris versicolor, it will replace by 0. If you have Iris setosa, it will replace by 0, as we discovered here. And also we are using the parameter in place is true. Once this replacement is done, the result should be retained in your data frame. So that's why we set the in place is true. We have to do the same thing for your ytest demo as well. That's what we are doing here. And then after we do that, let's do a count to double check whether our changes happen or not. We are doing the check with the ytrain demo. Okay, so now we know the changes were made. We have in the training demo, we had 0 with the class 0 with 65 items with class 0, 35 items with class 1. Ideally, you could do this in a different ways. You could call this even before. So let's try to do that at least. So I'm going to call this before we make this transformation to make sure we are doing the transformation correct. So before we do transformation, we should have Iris virginica 35, Iris setosa 34, and Iris versicolor 31. And then if after we execute, so that's how we can verify. So Iris versicolor is 31 plus Iris setosa 34 will make you 65. So that's the class 0. That's what we expect. And Iris virginica, we have 35 rows. So that's what we say class 1. So our transformation happened correctly. Okay, so we verified our binary variable transformation to build this binary classifier. So now you all know very well how to construct a logistic regression model. So this we are creating the model object and we are training the model. So we are training our binary classifier to predict whether your observation belongs to Virginica or not. So we trained the model and now we can verify the classes. Since our y variable became a binary variable which can hold 1 or 0, so now our predicted classes will be 0 and 1. Then the model coefficients, you will have only one row in your model coefficient matrix, so that indicates your one classifier you build within this one single binary classifier. And the intercept, you should expect only one item in the intercept matrix array. Okay, so this is a knot, so I would like to make it mark down. So let me. So what will happen? So this is one of the model you saw earlier. So there will be 3 such models built internally. Then each model will give probability to be in that class. The results of 3 models will be combined to give the final prediction output. That's what you get from the original model we built. 3 models will decide which class your observation should belong to. Okay, so that is part of another advanced discussion, but you have to understand now how the one versus rest or one versus all model work here. To give us the logistic regression model should be deployable in a multi-class classification problem solving. Okay, so now we trained the model and we also did some detailed understanding on one versus all or one versus rest method of creating a multi-class classifier. So now we have the classifier built. We wanted to evaluate the classifier, like I gave the example, how teacher evaluate you after you complete the course, whether you learn well or not by a final exam. So we wanted to give that final exam to the trained model. Like I mentioned earlier, what we are using for this final test is, or evaluation is the test sample, which is not being part of the training. Let's explore the test sample. We know what is test sample before. So we know test sample should contain 50 items or 50 rows. So then what we can do is I again like making an explicit copy as the test result just for future reference. And then the test result, I'm moving forward the new data frame test result to report the outcome of the model training. Means I'm going to predict for this test sample and create a new column with the predicted values. So first of all, I wanted to create a new column with actual value. If you notice, we have only 4 columns because we start with X test, only contain features. I wanted to add the actual values or the Y values for those test data set. Where we store the Y values earlier is Y test variable. So I'm going to assign it back to a new column and name it the column as actual. So let's execute this. And after execute, I will copy this test result down here, and I will call the head method to get my first 5 rows, and let's see what's going to happen. So it contains 4 feature columns and then the actual column which indicates the class. We know this as a ground truth from our data set. But we should assume for the model testing purpose, we should assume we don't know this and we use these features, what is the model is going to tell you, and then compare with this actual. That's what our test or our evaluation looks like. Okay, so now we have the features in the data set. So what we are doing is we are trying to make predictions. Like I mentioned, we are using the model we trained above, and then we are passing the X variables only. We don't pass the actual, remember that. And then we are trying to predict the probabilities of each class. So let's see what we get. Before we do that, I would like to show you what we get in this predict probability function. Okay, again the function is this is your model object, trained model object. You should have dot predict probabilities. This is a function of that model object, predict underscore proba, and then you pass X variables. You can pass any set of X variables matching the column names and the same dimensions as your trained data set. But here we are passing the test variable set. Here I had to make some change. Let me go back to the previous cells. So here we created a new model to demonstrate one versus rest classifier. So there I made a mistake. So I created that new model object also with the same name as our original model. So I had to rename it. So otherwise I'm not getting the correct model evaluated. Then I had to re-execute the code cell above. Once you're executing, you have to, if you will get the corrected notebook. But once you are executing, so you need to make sure your model object is named properly and you should not overwrite it after training. So that's what I made, the mistake I made. So I corrected it. So your original model is named as model, and then our demo to demonstrate a one versus rest model, I renamed as model underscore demo. Okay, so that's one change. You have to keep track of it. All right, so now let's go back to our prediction function. So the predict probability function. Okay, so the predict probability function will predict the probabilities for each class, for each row. So let's see what it is going to give you. You see, it returns a NumPy array with three columns, right? You see 3 columns, and number of rows should be equal to number of observation in your X-test data set. Here we should have a two-dimensional NumPy array with 50 rows and 3 columns. Okay, so what each column describes, so we know what each row describes. It's an observation. What each column describes the probability for this observation to be in each class. So what are these 3 classes? This is what we can get from our model parameter. So what are the 3 classes? Iris setosa, iris versicolor, and iris virginica. So they are in that order. Okay, so now we can use that. So let me collapse this. You can collapse the window here at the output, because we have 50 rows here. So now we can apply that, the predict function, and assign it to a new variable called probabilities. And then we can assign that new column, new 3 columns, right? So this probability will have 3 different columns. So we have to assign into our test result data frame as 3 new columns. So this is one way to do that. First, I will get the indexing, the limiter in NumPy arrays. You can say, give me all rows in 2-dimensional NumPy array. If you limit your indexes, if you wanted to slice your NumPy array, you can do that. Give me all rows but first column, or column index 0. And for this probability for iris versicolor, give me all rows and first column, so second column, index number 1 column, or the second column in the output, or the probabilities output. And for iris virginica, give me the third column, which is column index number 2, and all rows of that. So therefore we are slicing your 2-dimensional NumPy array output from the predict probability function, and then assign it to a column each in the data frame. So let's do that. So once you do that, we can also make the predicted column populated. So how you can do that? So your model is capable of now to predict not only the probability, it will predict which class this belongs to. So the function to do that is model.predict. The predict is the function. You have to provide your X data set, or the X variables or features. You can provide one feature or features data set with one row or multiple rows. In this case, I am providing entire test data set, and then it will predict which class it belongs to for each row. Once you do that, a new column will be created. So in this case, the predict function will not create multiple columns, but it will create one column only, or it will create an NumPy array, 1-dimensional NumPy array with classes, the predicted classes. you can assign it to a new column in your test results data frame we created above, and we can name that column as predicted. Now we created actual column and we created probability values for each class, and then we created a new column named predicted. So that will contain all the predicted classes for all the observation in your dataset or test dataset. So once we do that, we now have complete result set. So that result set contain our original features we send to, and we have the actual class each observation or each flower belongs to, and then from our model, the rest of the things generated from our model. So that model will tell you what is the probability of this observation or this flower belongs to this iris setosa, what is the probability this observation belong to iris versicolor, and this what is the probability to be iris virginica, and then your model also predict which class it belongs to. So we can also try to understand this from the three probability values, right? For iris setosa, we have really low probability, it's almost 0. And for iris versicolor, its probability can be 0.06. It's very low value. But for the iris virginica, we had 0.93. Or if we take into 100 as a percentage, so 93% chance of being iris virginica. So your model is obviously decided the predicted class is iris virginica. The second observation, you have 96% or 0.96 to be iris versicolor, and you have 0.01% to be probability for iris setosa, and 0.02 or 2% to be iris virginica, right? 2.0 to 2.5. So then what is the winner here, winner class here? So iris versicolor. So that's what you see. You can observe in your outcome. So you can observe your predicted class and also the probability values, and get some understanding how it decided the predicted class based on the probability value for each class. Okay, so this display all 50 rows, and I'm going to collapse this, and then let's try to go to the next part of our model evaluation. We learned about confusion matrix as a tool you can evaluate model. So this is not a model evaluation metric, but it's a tool you can understand how your model predict. Actually, the confusion matrix, we discussed this in detail. It will say how your model confused, how much your model confused, not how much you confused with the things we are learning or with the model training process, but how your model confused to make a prediction. So in this case, we can construct a confusion matrix using Pandas Crosstab function. You can also use the scikit-learn confusion matrix, but I prefer Pandas Crosstab because you can easily create a data frame out of it, and with a nice you can nicely present it. But the scikit-learn also provide you a good function. You can use it, that will generate a good print output as well. So I would recommend you to do that. So maybe in a future discussion I will use that. So let's use the Pandas Crosstab for now. So what you need to provide, you have to provide your actual column and your predicted column. I will enable margins to get the total values. So let me print it now, or execute the cell, so it will print the output. So what it tells you, it will show you what are the actual values in your row values, and what are the predicted values as your column values. So along the row iris setosa, we had 16 as actual flowers in our testing data set belong to iris setosa, and we had 19 for iris versicolor. We had 50 for iris virginica. From our predictions, we predicted 16 of the sample as iris setosa, and 18 out of the sample as iris versicolor, and 16 out of the sample as iris virginica. So we had all 50 samples in our 50 records in our sample. Okay, so how many of them predicted correct? That's the most useful information we can get from this confusion matrix. The next one is how much your model confused, or the errors. So we had all in diagonal are the correct predictions, right? 16 from setosa, and 18 from versicolor, and 15 from virginica. So altogether, these are the correct predictions out of the 50. We should have 49 out of 50 are correctly predicted. Your model worked really good. So one of the sample, one of the flower prediction was incorrect here. So that is in off diagonal. So that's what you had iris labeled as iris versicolor, predicted as iris virginica. So that's what you have, this one. So only one incorrect prediction, 49 out of 50 are correct predictions. Your model worked really good. So now let's look at some standard model evaluation metrics. Scikit-learn provide you functions to do that. So in previous lesson, I also demonstrated how you can derive some model evaluation metrics directly from the confusion metrics. But now I'm using the scikit-learn metrics functions to do that task. First, let's try to execute the cell and import the scikit-learn metrics. And then the second one we are going to do that is we are going to evaluate the accuracy score. Remember, the accuracy score from our lesson, the accuracy will define how many are in the diagonal of confusion matrix and divide the value by total number of observations. Here, what you need to provide to accuracy function in scikit-learn metrics is your actual value column, or you have it as an array. You can provide you as an array. And then you have to provide your predicted value column for each observation. And you can provide it as an array as well. Then scikit-learn will the accuracy score function will compute the accuracy score as we expected, 49 out of 50, which is 98% or 0.98 as a ratio. We can also calculate precision score, recall score, and F1 score. So let's calculate the F1 score using the scikit-learn metrics. Here I'm using the scikit-learn function metrics function called F1 score, metrics.f1 score, and then provide your actual column and your predicted column. And also I put a weighted average because we are using multi-class classification. So we have to use some kind of a non-binary way of computing F1 score and the precision and recall. So you can find out these details under our lesson on model evaluation. So we are going to discuss in detail about this different average methods and how we can use the F1 score, precision score, and recall score for a classification, multi-class classification problem, and how to interpret them. In this lesson, I'm not going to go to that detail, but I will show you how you can compute them in using scikit-learn for this problem. Okay, so I'm choose a weighted average, and then let's compute the F1 score. Okay, we got 98 point something or 0.98005, and let's go the precision score. So we get 0.98125 as my precision score for this model, and for the recall score we get 0.98. In very brief, precision will tell you if you predicted a value, how reliable that is. Recall will tell you if you make predictions, how many, or if from your predictions, how many good outcomes or how many correct outcomes you could preserve, right? So in confusion matrix we learn like the true positive and true negatives in binary classifier, but here all items in the diagonal will become true positive for each class. So to compute this recall and precision, we have to compute in a way like we can. That's why we use average for each class and then combine them to get the final value. So again, this part we will be discussing in detail with the model evaluation. So if that the slides are available to you, you can go back and revisit that. So or if not, if you are still did not look at it, so you can cover that in the coming lessons. All right. So let's go to the model performance. So once we evaluate the model, so now we build the model, we evaluated the model, and then we have to preserve it for future use. So we don't not only the model, but we need to know about the model training process in future, right? So if you build this model, if you save somewhere, you want to know how you build the model and what type of things you did, like many details about it. So you have to document it. So one of the main tasks of the machine learning model building is to document your model building process. If someone or you or someone wanted to build it in future, they should follow that recipe and rebuild it, or maybe improve the model, or maybe run the same model with different set of training data set. So maybe your training data set can be improved with the time, right? So you get more data to train with. So more data you used or more examples you provided to the model to train will make your model work better in most cases, if depending on the quality of your data. And then in that case you have to document it. You wanted to know what are the performance evaluation results and how many training samples you used, and maybe it's a good idea to save your entire training data set and testing data set for future testing purpose, right? But here, like I'm just demonstrating one piece of information you can store as a data frame if you want. So we have to say what is the model. So my end goal is to construct a data frame. So that data frame you can save as a numpy array, or Excel file or CSV file, or you can save as any data frame compatible format, or you can send to a database or in a SQL server. So here I'm going to construct it with this the parameters. Model name, so we can give a meaningful name. We can have some serial number, date, or anything to that model, so to identify the model uniquely. If you're building hundreds of models, sometimes in one project also you need to build more than one model. So in the next lesson we are going to discuss using the same data set, we are building a different model using a different algorithm called random forest classifier. So then we can compare this model with the new model we built in the next lesson. Therefore, we need to have a model name to distinguish between two models or multiple models you build. And then we record how many training samples were there and how many testing samples were there to train on test. And then what was your accuracy score for this model, and what was the precision score, what was the recall score, and what was the F1 score. So these things you can always compare in a future training. If your future training, or maybe a different algorithm you use to train, or maybe the same algorithm with different set of parameters, we will discuss about hyperparameters in a later lecture or later lesson. In that case we can always compare it. So if you wanted to choose another model over this model, those performance should be better, right? So that's the purpose of storing this data or preserving this data. Okay, so let's execute. And then this will create only one row because we have only one model, but it contains some useful information, right? In that row, train test size and the accuracy score, precision score, recall score, and F1 score. Okay, so now we are at the very last step. So that is saving the model for future use. So you create a model, you have to save it. Otherwise, when you wanted to make a prediction, you have to retrain the model. It's okay for this small model, or smaller in the sense like we use small number of records to train the model, therefore the training is much faster, right? And another thing I said small is number of variables. You use only 4 features, only 100 data records, right? Or 100 training size training data set. So that's a small data set compared to what you will get in a real project. So you will get much more variables and much larger training data set. So those training process will take time, sometimes minutes, sometimes hours. Therefore, it's not convenient for us to keep the model trained all the time. Therefore, we can save the model once we train. So once we have the saved model, we can always load it to memory and then use that model within like few seconds. So that's the purpose of saving the model. To do that, I'm using the Python library called joblib. So that will allow you to save that file in a binary format. So for that library, I need to provide, for the saving process, I need to provide a file name or file path. So I'm providing models/model iris LGR. I put LGR stand for logistic regression because we will be training another model for the same problem. So we have to make a different name. So I make this LGR as the name, append the LGR at the end of the name. And I use the joblib. It's not a standard extension. You can use anything as you want, but to make sure I know this file is created with joblib, I try to keep the extension joblib. Okay, so nothing fancy. I'm going to execute that, and then it will return you the file name and as the output. It will simply save the file into your disk. If we check on the folder, now we can see the model is now visible. So let me check the folder. So we have now saved the model object. So this is what we saved. Now do one test to load the model and see whether the model is loaded properly. So now I'm trying to call a different function, joblib.load. Okay, so I forgot to mention the function we used to save is joblib.dump, and then the model object you wanted to save and the save file path. To load the model, you have to use joblib.load and then give the file path of the file you saved. So I'm going to give the same path because that's the same file we are going to load. And then I will have the model object variable as model underscore, not to override the model we created above. So let's execute and verify whether our model can be loaded properly. Okay, congratulations. So if you come to this stage, you created a model for this iris flower classification to use classify your iris flower. Is a multi-class classification problem. You created a logistic regression model to do this multi-class classification, and you did the model evaluation, and then you saved the model and you verified your model can be loaded. So everything is done, so your model is ready to use. Previously, we discussed how to build a classifier to classify iris flower dataset, which has three different classes and 150 entries or 150 records from different flowers. We used logistic regression algorithm from scikit-learn to build a multi-class classifier. Now we are going to build another classifier using random forest classifier for the same dataset. Then we will try to combine the model evaluation results and compare them together. And then we will see which model is the best model out of logistic regression and random forest classifier. This is something we should expect to do in a typical machine learning project. You are building several models and then evaluate and find out which model should be the best for your application. So let's move forward with that. As a revision for our understanding about the dataset. So here I have a sample from the dataset. I picked like 5 sample rows, randomly picked them, and then the dataset contained feature columns, sepal length, sepal width, petal length, and petal width. The class labels or the target variable we use in this classification problem is flower class. So you can see 3 different flower classes. And all the variables or features are numeric variables in floating point numbers. You can see one instance belongs to iris versicolor, and you can see the image of the flower and how the features were extracted from the flower. If you wanted to know more about the dataset, you can go to the beginning of this lesson, which we discuss about the dataset in detail, and also you can read the article provided by this link. If you wanted to know more about Python or any other libraries such as NumPy, Pandas, and Matplotlib we are using, you can go to their documentation. We also have the link provided in this notebook. Okay, so let's load the notebook again because we are using a new new notebook. So I'm going to load the dataset from UCI Machine Learning repository. And previously we discussed how we can load the dataset from scikit-learn built-in datasets. So I'm not going to continue discussing on that. So then moving forward with the second section of this notebook, which is separating your X variables and Y variables. In the previous diagram, you already saw how you can separate X variables and Y variables and from the dataset. So we had to do that programmatically. There we created 2 variables. First variable, X variable, contain a list of strings containing column names to be used as X variables. Second variable contain a string containing the column name you should be using as your Y variable or target variable. So let's execute those. And then we will look at how to do the train test split. So we already discussed this in detail in our previous discussion about logistic regression multi-class classifier. So I gave some description about the train test split and also some more explanation about why we are doing train test split. If you want to listen to this again, you can rewind back and listen to that description. Okay, so I will do the train test split using scikit-learn train test split function, and then we will check what are the train and test sizes. Okay, so we have 100 rows or 100 instances in the training data set and 50 instances or 50 rows in the test data set. So let's try to train the classifier. So here we are going to train a random forest classifier from scikit-learn ensemble module. First, we need to import the random forest classifier class into our programming environment. So we are importing using this statement, and then we are going to build the model object or create the model object. Here we are going to provide some parameters. So the first parameter indicates how many estimators. We learned how to construct a random forest classifier using number of trees built together. So here we are using we are building 100 different trees using our sample dataset and making predictions of them, and then later we are combining them together to make the final prediction. So if you wanted to review that lesson about random forest classifiers and also the tree classifiers, how you make the decision from a tree classifier and how those decisions from a number of trees contribute to the final decision for random forest classifier, please review the lesson on random forest classifiers. Random state is a variable you can set any number, so that will define the seed value for this algorithm to begin the random state. And the max depth and min sample split are also parameters you can control the behavior of random forest classifier. The max depth 10 indicate you can go up to 10 levels deep in the trees in each tree you are building. Min samples to split will indicate how many minimum number of samples should be in one leaf or one node to split it further. Since we have a small number of records in this dataset, I would set this value to 2. It's obvious you have to have at least 2 to split a node or leaf further, but you can set to a higher value if needed. Okay, so once we created the model object, we can call the fit function, and also we have to provide our xtrain, which is our feature variables for training data, and also we need to provide ytrain, which is our target variable for training data. Okay, so we are providing the training data and calling the fit function, and then we will try to train this model using our training data set. Okay, so the model is now trained. Since this is a small number of samples available and a few features, so the training process is much faster. In a typical data science application or machine learning application, you get a large data set with large number of columns and large number of rows. In that case, your training process will be lengthier, so it will take some time, maybe minutes or maybe a few seconds. Sometimes it can take several minutes, like hours. And then we will go to the model parameters. So we build the model now, we train the model, and now we can observe or we can extract some of the parameters of the trained model. What are the parameters available in scikit-learn random forest classifier? So we previously looked at what are the parameters available with the scikit-learn logistic regression classifier. So a few things you can extract from this model object. Features. The model.feature underscore names underscore in underscore. So that is an attribute of the model object. If you call that, or if you type that in an expression, it will return number of list of features you are going to use in this model or you used for the training. So let's execute this cell and let's verify whether we get it correctly. As we expected, we get the list of 4 features we used. Those features are written as an array. You see the 4 features as we already identified. And the next attribute you can get from the model object is classes. Classes underscore will be the attribute name. If you call that attribute, that will return names of the classes you used in this model. So here we have 3 classes. So we can extract these 3 classes in from the model object directly. So now you have to understand the model object. When you create, it stores the feature names and the class names inside the model object, so you can later access them. Later we will learn how to store the random forest classifier model in the same way we did saving the logistic regression classifier. You can also access these classes and features in a later time if you save the model object. Okay, so now let's look at another important function comes with the model object. So this function method will give you all the parameters you use to train the model. If you wanted to see the parameters, or if you wanted to report which parameters used, you can call the get params. So that will return a dictionary with keys as the parameter name and values as the parameter value you set for the training. This is not the parameters you use to fit into your data, but these are the parameters your algorithm use. So we call sometimes these are hyperparameters. Not all of them are considered as hyperparameters, but some of them are. So like n estimators, and whether the max leaf nodes, minimum max features, max depth, and also the criteriation. So those can be considered as hyperparameters. So later, when we are discussing about hyperparameter tuning, we can discuss how we can change these values and how we can train your model differently to meet high performance standards. Means your model will be, you predict better than some other parameter combinations if you use like the optimum parameter combination of each. So we will find ways how to discover that optimum combination of parameters to get the maximum outcome of that model in a later lesson. All right, so then if we wanted to visualize the trees, so now recall again about the lesson we discussed random forest classifiers and the decision trees in general. So imagine now the tree diagram of the decision making. If you wanted to visualize the actual tree diagram used by the model, now you have to assume we have 100 different trees in this model. If you wanted to visualize all 100 trees, it's possible, but it will need like a lot of space to print the output. So if you print it here, it will be so very lengthy, Jupyter notebook. Therefore, I'm not going to print all trees as the diagram, but I'm going to print the first tree and last tree as an example. So how you can get individual trees out of the random forest classifier model object? It's easy. So what you need to do is you can have to say model dot, that is your model object, and then you can call the estimators. It's an attribute. So if you take the estimators out of the model object, that will give you a list or an array of items. Each item is a tree classifier. It's a decision tree classifier. So you know what is decision tree classifier from our previous lessons. So this contains 100 different trees. The estimators will return you 100 different trees in an array. What you need to do is you need to provide an index to get one tree. So here I'm providing index 0 to get the first tree, and I'm providing index number 99 to get the second tree. Sorry, 100 tree. So that's why I name it tree 1 and tree 100. So now we get 2 trees out of the model object. So now our task is to plot them and visualize how each tree will make the decision. To do that, I'm going to use scikit-learn from the scikit-learn library. There's a class called tree. So in tree, you can call the function named plot tree. So this plot tree function, for the plot tree function, you need to provide a decision tree object from scikit-learn, and then you have to provide feature names. You can provide list of features, and then you have to provide class names. This information we already extracted in our previous steps. You can go back to the notebook, above cells in the notebook, or you can rewind the video and check how we extract those values. The x variables we already set manually, and also you can consider the features as the x variable, the variable we extracted from the model object. Then if you wanted to use the color and everything, so you can use the fill true, and then the axis. So this is from matplotlib. We are creating 2 axes. So we are plotting the first tree plot in axis 0, first axis written from the subplots, and then the second plot for the tree 100 we are going to plot in the axis 1 or ax1. So these are 2 axes written from this matplotlib subplots. I'm not going to go into very detailed discussion about subplots. This will be another discussion for Python and visualization using matplotlib. So here the subplots will create a grid of plots, which number of rows is 1, number of columns is 2. And I set the figure size to 20 by 10. So to make sure it will fill up the space in this notebook, and then you can visualize and read the trees clearly. Okay, so read whatever the printed content with the trees. So let's try to execute and then see how your two trees make the decision. Okay, so now we have two trees printed or the displayed in the notebook. So the first tree will use some conditions. So if we provide the petal width, so if the petal width is less than or equal to 1.5, it will go to this branch. And if the petal length is less than or equal to 0.6, it will go to the other branch. Like that, it will go through the decision tree path and finally end up with a decision. Okay, so based on where it is going to stop, you can find out what is the final decision, and also you can get the probability of the final decision by combining all these 100 trees. In random forest classifier, we'll learn in detail in our lesson about random forest. So each tree will contribute to the final voting. If you have 100 trees, if 50 of them are voted for a different class, another 10 of them voted for another class, and another 40 of them voted for the third class. So we have to choose the class it voted the most by most trees. That's how you can get the probability value of each, and then you can finally get the decision coming from an ensemble model, which is combined result out of all 100 trees. All right, so you can read more about this tree and how to interpret this diagram in a different lesson. Okay, so now let's try to evaluate the model. So now we have the model created. We try to visualize the model in tree diagrams, at least two trees out of this 200, two trees out of the 100 trees we built. So we try to visualize it, and then we want to evaluate the same way we evaluate logistic regression classifier, because we wanted to know how good your model is. That is the main goal of model evaluation. To do that, we need to construct the result table. The result table should contain your test data set, their actual values or ground truth for the flower class, and then we wanted to know what are the predicted values given the features of each test data point. So first to create the test result set, so let's try to make a copy of X test, so which only contain features. There's no target variable. Remember, the X test don't contain any target variable, so therefore it contain only 4 features. So we make a copy of the data frame and create a new data frame object named test result. So in the test result column, we don't have the target variable. Therefore, we are creating a new column, named it as actual, and assigning our y test y test column, right? Because we need to have the actual column in our test result data frame as well. So this will do those things. So before that, I just run this one, and then we have to verify. We can verify how many rows and how many columns in X test. We know it's 50 rows and 4 features, and then we will use the data frame object here, and from now on I call test result, and we assign a new column y test we named as actual. So then we will make predictions. So how to make the prediction? Same as the logistic regression classifier, you can say model.predict. So it will simply make a prediction. So that model.predict will tell you what are the predicted class for each observation, given that the features. So given 4 features, the actual value, not given 4 features, the actual value for these 4 features is Iris virginica. Given these 4 features, the predicted value is also Iris virginica for this instance. Let's see if they have any mismatched ones. So these are like predicted correctly, right? So we don't find any incorrect prediction in this example. Let's see if we can find any. Okay, by the visual inspection, I still don't see it. We have to have few. Found one. This one, this record predicted as iris versicolor given the features from our model, but actual class belongs to iris virginica. This was an incorrect prediction. All right, so I think our model worked well, but we wanted to quantify, we wanted to know further about how your model worked. We will use a confusion matrix to evaluate our model. So let's see how your what details your confusion matrix will going to provide you. We discussed about the confusion matrix in our previous discussion about logistic regression classifier and how the confusion matrix can help you to determine your prediction and also get some idea about how good your model works. Here we have two incorrect predictions from the first observation, right? So one prediction was actual value was iris virginica and predicted as iris versicolor. And another incorrect prediction was initially was iris versicolor predicted as iris virginica. Those who are in the diagonal are correct predictions. So now we have 48 out of 50 are correct predictions. 2 out of 50 are incorrect predictions. Therefore, now you can do a hand calculation or you can calculate in your mind what is the accuracy for this data set or this prediction. So obviously is 96%. 50 out of 48 out of 50, 96% or 0.96. But we will try to quantify using scikit-learn library functions. Okay. To do that, we have to import scikit-learn metrics, and from those metrics we are going to use accuracy score function and provide the actual column or as a pandas series or numpy array, and then the predicted column which can be provided as a pandas series or numpy array. Then the accuracy score will compute and you can get the value. As we expected is 0.96 or 96%. Let's look at F1 score. The F1 score, we had to do the same. We provided actual column and predicted column, and since this is a multi-class classification problem, we will provide average is weighted average for each class. Because F1 score you can calculate per class, but if you take weighted average, so you will get the overall F1 score. Same thing we can do for the precision score. We can call the metrics.precision score function, provide actual and predicted columns, and we also set the average as weighted, because precision also can calculate per class, but we can calculate an overall by doing the weighted average. Precision also 0.96. Let's do the same thing for recall using metrics.recall score. The same parameters, actual column, predicted column, and average is weighted average. So let's execute that. 0.96. So we get all values are 0.96. We have the precision, accuracy, F1 score, everything are 0.96. In a typical machine learning problem, you probably not get all the values are the same. So this is a textbook example of like to teach machine learning to understand the concept. So this example worked really good. Therefore we get 0.96, but in some real application, you get a variation of values for each of these metrics. Based on the metric value, you have to decide what metric to be optimized when you are tuning the model to perform better. Okay, so let's go to a model performance dictionary or the data frame we are going to create, same as we did for the logistic regression classifier model. So we will to create a model evaluation report. So we are going to create a dictionary of model evaluation result. We explained this in detail with our previous discussion on logistic regression classifier, but I will briefly introduce you that. So we have to provide some description about the model. The model is you can give a model name to for future identification, any identifier. You can create more keys and attributes. This is not a standard way of creating the evaluation report, but you can add more things if you need. But those are some essential thing I think at this stage you should add. how many samples you use to train, how many samples you use to test, what is your accuracy score, what is your precision score, what is the recall score and F1 score. This will be useful in a later time when you wanted to revise the model or you want to track the model performance over time before you make any changes. So using this dictionary object, I'm going to create a data frame. So this data frame is nothing fancy. It will have like only one row with all the columns will be our report parameters. So now we have created the model and we can save the model for future use, same as we did for our previous model. We are using joblib library. We are providing path name to save the model object, and we are using joblib.dump, which is the library function from joblib library to save a file into a binary, save a Python object into a binary form, which is like a pickle form. So if you call this function, you are dumping or you are saving the model object in binary form in a pickle file. So that file is named as model iris rf joblib. And then for the second parameter, you have to provide this path. Okay, so if we execute this, you will see it returned a result with it returned the file path that indicates that your model save happened. Let's try to our folder location and see whether our file is properly saved. Okay, so now we see our new file called model iris rf.joblib. That is the new file we created. So that file is being saved. And previously we saved the logistic regression model under this name. So we have both models from this lesson saved properly. Let's go back to the notebook. We are now at a stage. We build the model, we evaluate the model, and then we also save the model into the disk and we can use it later. And now we can do comparing two models we built in this lesson. First we built logistic regression classifier and then we built the random forest classifier. We have both models saved into files in our folder location. But we can use the model in memory, which is the random forest classifier model we already have loaded, and then we can use our logistic regression classifier loaded from the file, and then we can evaluate the model again. So let's prepare the dataset for the model comparison evaluation. I'm using the same test dataset, so therefore I'm making another copy of my test dataset. So into test result data frame object, and then I'm repeating the same step we did above and creating a new column in the test result, which is then assigning y test an NumPy array which contains the actual values of your each observation. And then I'm going to evaluate the logistic regression. So how you can do that? Because we did not train any logistic regression in this notebook. What we did was we previously trained that model and we saved. We know the model path. So here I'm providing the model path of the saved model location. And then I'm calling the joblib function named load, and then load function, you need to provide your model path. So once you provide model path to joblib.load, it will load logistic regression model and into the model underscore LGR. So that's what our model variable name is. And then what I'm going to do is I'm going to predict the result for the from the given observation in the test data set. I'm going to use model LGR.predict function to predict the outcome. So let me execute those cells. So first I load the model. So model is loaded now. And then what we can do is we can use the predict function. So let me go above. We did not execute the cell above as well. Let me execute these cells. Otherwise we will not get the result as we need. So we execute this. And then we can get the accuracy. So we execute this cell to predict, and then we run the evaluation matrix. I accidentally ran the evaluation matrix cell as well. So the predict function will populate a new column called predicted. So using that predicted column and the actual column, which was the ground truth we assigned earlier into the dataset, And then we can compute accuracy score, F1 score, precision score, and recall score as we did before for this logistic regression model. And then we can create a dictionary object for a logistic regression model evaluation result with the model name. So I call this model name as LGR for logistic regression. Previously, we created another dictionary object named model we named as RF, and we gave all the parameters: test results, train size, test size, accuracy score, precision score, recall score, and F1 score. So we can keep that dictionary object for future use. Okay, so now we can do the same thing for random forest classifier. First, we load the model object. Then we can predict. After we predict, we can assign the result to a new column in the test result set. And then we are using scikit-learn metrics, accuracy score, F1 score, precision score, and recall score functions to create those evaluation results. So those results I'm going to assign into a dictionary. So I'm creating a new dictionary, metrics comp underscore RF for random forest classifier evaluation results. So now we have two dictionaries created with the evaluation results from each model. Now we are trying to compare those two models. I would like to create a data frame because data frame will help you to visualize and analyze data more efficiently. Therefore, I'm going to convert this dictionary into a variable into a data frame, and then that data frame should contain two rows. One row belongs to logistic regression model with the evaluation parameters and model training parameters, and the second row should contain the same for random forest classifier. We see now logistic regression and random forest side-by-side comparison. So what do you think? Which model you should be using? From this exercise, we found out logistic regression worked better than random forest classifier. We get 98% accuracy or 0.98 accuracy versus 96% from random forest. For precision score, it is also 98% versus 96%. Recall score is also 98% versus 96%. We can also say 0.98 versus 0.96. F1 score also we got 9.98 or 98% versus 0.96 or 96%. Which model you will be choosing now based on these numbers? It's obvious. I would go for logistic regression because it has the best accuracy, best precision, best recall, and best F1 score out of these two models. In a typical machine learning project, you should build like number of models with the same algorithm with different hyperparameters. You are changing some parameters to change the behavior of the algorithm, and you will be expecting different evaluation results. You can use the same dataset. You must, otherwise you cannot compare apple to apple, right? So if you do that, you will get different evaluation results. Based on that, you can choose which model from the algorithm you choose should be used in your application, or which model you should move forward in your project. If you're using multiple different algorithms, like in this case logistic regression and random forest, you can use different algorithms for classification problem, and then you can compare them and find out which algorithm suits the best. And in a typical project, we will use both methods. So we are using the same algorithm with different hyperparameters, build several models, and also we are using different algorithms, and also in each algorithm we are doing the hyperparameter changes, and then we are trying to find out which algorithm with which hyperparameter combination will give you the best result. To systematically do that, we will explore how to do that in hyperparameter tuning lesson. You can use grid search or random parameter search methods to do that. So we will learn how to do that in a future lesson. Until then, so let's try to recap what we did. In this lesson, we trained a logistic regression classifier, a multi-class logistic regression classifier for iris flower dataset to predict 3 classes from 150 observations available to us. And then second, we use the same dataset to train a random forest classifier, and then at the end we try to evaluate 2 models and compare them together and decided which model should be used in our next stage of the project or which model we should be move forward. I hope you learned something from this lesson and see you all in the next lesson. Thank you.